Hello, everybody, and welcome to Chapter 9 out of Contemporary Nutrition. This lecture will cover water and minerals. Water makes up, I'd say, about 65% of our body weight. Muscle contains about 73% water, while fat contains approximately 20%. Where does this water lie? Well, there's intracellular fluid, which is the fluid within cells, and extracellular fluid, which is the fluid outside of cells. One of the things to note is that fat contains far less water than muscle or connective tissue or even epidermal or dermal tissue. And the reason for this is that fat is hydrophobic, which means it's water-fearing and it tends to associate with other molecules that are nonpolar. And a nonpolar molecule is simply a molecule that doesn't have a separation of charge on it. So basically, the electrons are distributed evenly around the surface. Examples of nonpolar molecules would be things like fats, oils, cholesterol, things that are essentially greasy. So they tend to exclude water, and that accounts for the much lower percentage of water in adipose tissue. If we were to look at how osmosis works,
diffusion is the net movement of molecules down a concentration gradient. This process allows small molecules, such as oxygen and carbon dioxide, to cross the plasma membrane. Most polar molecules, such as sugars and proteins, cannot freely cross this lipid membrane. Although water molecules are polar, they are small enough to pass through the membrane freely. This special case of diffusion that involves the movement of water molecules across a membrane is called osmosis. If a molecule, such as urea, is added to one side of a membrane, it will not be able to diffuse across the membrane because it is both large and polar. Because of its polar nature, it will interact with other polar molecules such as the water. This interaction reduces the number of free water molecules on the right-hand side. With fewer free water molecules on the right-hand side, there is now a net movement of water molecules down their concentration gradient to the side with the urea molecules. Because more water molecules are moving into this area than are leaving, the water level on the right side will rise. If the osmotic concentrations of two solutions are equal, the solutions are isotonic. However, when the solutions have unequal osmotic concentrations, the solution with the higher concentration of solutes is hypertonic, and the solution with the lower concentration of solutes is hypotonic.
water shifts freely in and out of cells, and it's controlled by electrolyte concentration. Osmosis is the driving factor, and remember that when we're talking about osmosis, we're talking about the flow of water down its concentration gradient, and this is driven by the principles that govern the second law of thermodynamics, which states that given no energy input into the system, objects will tend to arrange themselves in the lowest energy configuration. And so what water tends to do is it tends to flow away from an area where it's highly concentrated towards an area where it has very little concentration. So in the video you saw that water tends to chase solutes in an effort to equalize concentrations of solutes and water on either side of a semipermeable membrane. Intracellular water volume depends on intracellular potassium and phosphate concentrations, while extracellular water volume depends on extracellular sodium and potassium concentrations. And what we want to remember is that, again, water will follow where the solutes go. This is a process that doesn't require any input of energy. It is simply an outcome of osmosis. You might ask, well, how is it that these electrolyte concentrations are maintained on either side of the cell membrane? And the way that's done is through protein pumps that are embedded in the cell membrane that are constantly running and using ATP to separate charge so that the inside of the cell is negative compared to the outside. And what that represents is a form of stored energy that your body can use for performing various housekeeping cellular activities, but it's also extremely important in nervous tissue and muscle tissue where this membrane potential is used to either conduct nerve signals or to allow muscle tissue to contract. So, if we look at a typical red blood cell, what we see are three scenarios here, with the cell in a hypotonic solution here, in an isotonic solution here, and in a hypertonic solution on the far right hand side. And what I want you to note is that the movement of water is dictated by the concentration gradient of water in each state. Well, if you look at the hypotonic solution, this is a cell that's immersed essentially in distilled water, and as a result, water is more highly concentrated outside the cell than inside. As a result, it will tend to move into the cell through the plasma membrane, causing the cell to expand and eventually explode. In an isotonic solution, what you have is no net movement of water across the cell membrane. Water is entering the cell as quickly as it's leaving it, and as a result, there's no change in cell volume. In a hypertonic solution, what you have is a concentration of solutes outside the cell that's higher than inside the cell, and what will happen essentially is that the cell will dry out. Water will, in an attempt to dilute the extracellular environment, will leave the cell, causing it to shrivel and crenate. So it's very important that electrolyte concentrations be properly maintained, and also that we have adequate water to compensate for our water loss. And we'll talk about water loss here in a minute. Let's talk about what water does. It regulates our body temperature. Water absorbs excess heat, and the body secretes fluid through perspiration, and your skin is cooled as the perspiration evaporates. And the reason that it cools is because as water transitions from a liquid to a gas, it takes with it kinetic energy, and we experience that as a loss of heat. So what will happen is that the skin surface will cool. By extension, the blood vessels that are at the skin surface carrying our blood will cool as a result of being in contact with the cooling skin, and that will result in a cooling of our overall body temperature. So this is one of the ways that the body maintains homeostasis. This is why you sweat when you're in a hot situation. This is an attempt of your body to try and keep your temperature at 98.6 degrees Fahrenheit. We also lose water as waste in the urine stream. We excrete the breakdown products of protein catabolism, which are urea. We also excrete sodium as needed. If sodium becomes overly concentrated in the extracellular fluid, we can excrete it at the kidneys. As we're breaking down protein, we're constantly removing the excess nitrogen through urea excretion. We want to avoid, in general, a condition that causes us to excrete constantly concentrated urine, because what that indicates is that we're losing water volume to the environment, and that can lead to such conditions as kidney stones, gallstones, and in some cases gout. So it's always important to remain as hydrated as possible so that your intake equals your output. Your amniotic fluid, your joint lubricants, your saliva, and your bile are also primarily composed of water. And so, again, these are some of the important biological functions that water is an absolute necessity for. Okay, in the next slide, what we're going to see is some water content of foods, and so you can get some idea where your water comes from. It's not simply from drinking water, it's from the consumption of food, beverages, fruits, vegetables, and meats. So take a look at this upcoming video. Okay, what we're looking at here is a slide indicating whether or not you're drinking adequate water to equal uh, your water loss. So here we see in a typical individual, you take in about 2.8 liters per day to equal an average water output of 2.8 liters per day. And obviously, if this is out of balance, if we're losing more than we're drinking, we'll dehydrate. If we're drinking more than we're losing, which would indicate a problem with the urinary system or perhaps a problem with loss of water through sensible perspiration and insensible perspiration through the skin. That would result eventually in tissue edema and electrolyte imbalance. So, in normal individuals, this isn't the case. The urinary system and transpiration and sweating work as they're supposed to, and so generally our water intake should equal our water output. Fluid recommendations are 9 cups for women and 13 cups for men as a starting point. Men require more because men generally have a higher metabolic rate than women, and one of the products of metabolism is water. If you remember, glucose plus oxygen goes through many steps inside the cell in oxidative metabolism, and the end products are energy, CO2, water, and heat. And so water is always a result of actively metabolizing tissue, and this accounts for the difference between men and women in terms of their water requirement because of the enhanced metabolic rate, which is in part fueled by testosterone. Your thirst mechanism is not always reliable. This brings up concerns for infants, older adults, and athletes who should weigh themselves before and after a training session and consume about 2.5 to 3 cups of water for every pound they lose as water weight to avoid dehydration. We can also lose water through illness. Vomiting or emesis, diarrhea, and fever can result in water loss in the waste stream, and the danger there is not simply dehydration but also the loss of electrolytes, which, as we stated before, can interfere with membrane potential, which can affect muscle contraction and nerve conduction, among other things. If we ignore the thirst signal, we get into trouble. A shortage of water usually increases fluid conservation in this case, so the body's trying to keep itself alive. There are also hormones that control water balance. Antidiuretic hormone, nicknamed ADH, is released by the pituitary and forces the kidneys to conserve water by reducing urine flow. Diuretics are a class of drugs that dehydrate you. So when you think of antidiuretics, such as ADH, think of a hormone that causes you to retain fluid. Another fluid retaining hormone is aldosterone, which responds to drops in blood pressure by signaling the kidney to retain sodium, and the net result of that is that the water will follow the sodium and remain in the body. So aldosterone and ADH are both water retaining hormones.
Hormonal communication generally begins with a part of the neuroendocrine system receiving sensory information and reacting by issuing a command to the body in the form of a hormone. In this example, dehydration is detected by osmoreceptors in the hypothalamus, which then directs or stimulates the posterior pituitary gland to release antidiuretic hormone, ADH. The next step is to transport the hormone molecules to target cells. This is typically done via the bloodstream. Here, ADH is transported through the bloodstream to the kidneys and blood vessels. When hormone molecules reach target cells, they will bind to matching receptors on those cells, and the hormone receptor complexes will trigger changes in the target cells. This causes the kidneys to reduce the urine volume output, thereby increasing water retention and countering dehydration. In blood vessels, vasoconstriction is increased, leading to higher blood pressure and thus countering the blood pressure drop caused by dehydration.
We lose about 1 to 2% of our body weight in fluid. This sets off the thirst signal. Loss of more than 2% or more of body weight causes muscle weakness, and we lose significant strength and endurance as a result. A loss of about 10 to 12% can result in heat intolerance, and a loss of 20% would result in coma and death. And what we're looking at here is simply a table that shows you the different levels of water loss, the category into which they fall, okay, and the recommended servings per day to avoid water loss. So what we're seeing here is that obviously the most efficient way to rehydrate yourself is through the consumption of water, followed closely behind by dilute unsweetened beverages, and then behind them milk and soy beverages, non-calorically sweetened beverages such as diet drinks, and then calorie-laden beverages such as Coca-Cola, Sprite, 7-Up, and so forth. Also sports drinks. And then calorically sweetened beverages that contain alcohol, mixed drinks and such. Okay, so obviously you're going to get the most water with drinking simply water. So this is the most efficient way to meet your daily water requirements. But remember that we're constantly consuming water in the food we eat as well. So take that into account. What can happen with too much water? You can overburden the kidneys. This can result in also low blood electrolyte concentration and blurred vision, and it can kill you. We talked a couple of weeks ago about the fact that every compound that you eat has an LD50, which is that concentration of compound that will kill 50% of the test subjects studied. And water also has an LD50. And if you consume too much water in too small a period of time, you'll dilute your electrolytes, and the result will be problems with nerve transmission, problems with muscle contraction, and it can lead to death. So again, we want to stay within a window, right? You don't want to drink too much water. You don't want to drink too little water. You want to equal the amount that you lose through normal metabolic processes, normal physiological processes. Okay, where does our water come from? We get most of it out of our tap here in the U.S. The Safe Drinking Water Act was put into place by Congress to monitor the water supply for bacteria, chemical, and toxic metals. Our U.S. water supply is among the safest in the world because we have very, very good water purification plants in most major metropolitan and rural areas. Water goes through a series of purification steps before it enters our tap and is safe to drink. So nothing to fear from the water coming from the tap. Bottled water is often used by individuals in lieu of tap water, but to be honest with you, tap water is perfectly safe. It may contain a few metal ions as a result of flowing through pipes, and it is of course chlorinated and fluorinated to retard bacterial growth, but above and beyond that, there are no ill health effects from drinking tap water, so I recommend it highly. Okay, minerals have various functions in the body. Our major minerals are required in amounts greater than 100 milligrams per day. Examples would be calcium and phosphorus, which are major components of the skeletal system, but are also important in other metabolic processes, such as nerve transmission and muscle contraction. Trace minerals are required in amounts less than 100 milligrams per day. Examples would be iron and zinc. And just because they're required in smaller amounts doesn't mean they're any less important in the body. For instance, iron is a trace mineral, but if we were to consume iron, if you were to remove all the iron from our body, we would probably die because iron is an integral component of hemoglobin, which carries oxygen to metabolically active tissues. And there are numerous examples of trace minerals that are vital to our very survival. Examples given here are iron and zinc. And what we're looking at in the next slide is simply a typical human body broken down into mineral components. And so what we're looking at are grams in the typical human body, and then the mineral listed, or for the chemists in the class, the chemical listed. Okay, mineral is simply another name for a chemical. Chemical is a pure substance made up of one type of atom. So here you can see that calcium and phosphorus predominant, followed by potassium, sulfur, sodium, and chloride, and magnesium. And then once we get to the trace minerals, examples would be iron, manganese, copper, iodide. There's other trace minerals as well that aren't listed. But again, just because they're present in smaller quantities doesn't mean they're any less important to our normal physiology. Okay, bioavailability of minerals is dependent on degree of absorption, the presence of binders and fiber, the animal products in our diet, which are often better absorbed than plant products. Plants depend on mineral content of the soil, and refinement can lower mineral content in any type of food. There's also mineral competition in the foods that we eat, where um, ions that have a similar charge and a similar size will compete with each other for slots on the absorption pathway. So you want to be mindful of that in the foods that you consume. And there's also a competition between vitamins and minerals, because often vitamins and minerals go hand in hand as coenzymes, and sometimes one is favored over the other. Okay, like anything else, minerals have a toxicity. They have an LD50. Trace minerals generally tend to be more toxic. Uh, Supplementation can lead to mineral toxicity uh, through a couple of methods. One is simply too much of the trace mineral, but also is the presence of contaminants in certain supplements. What you want to look for are the USP approved brands of supplements to avoid these types of problems, and you want to avoid megadosing on any specific mineral. You want to look at your RDA, and you want to avoid your upper tolerable limit, okay, by probably a factor of at least 5 to 10 fold. Okay, sodium is one of the most predominant compounds in the U.S. diet. It's made up of, it's primarily found in the U.S. diet in the form of sodium chloride, table salt, which is 40% sodium and 60% chloride. 95% of the ingested sodium is absorbed. It becomes a positive ion in extracellular fluid. And remember that aldosterone regulates sodium balance, and it's the key for retaining body water. Excretion is regulated at the kidneys, so the kidneys will either excrete more or less sodium depending on what we consume. And it's also a very important ion in muscle contraction. It is, in fact, one of the ions that initiates muscle contraction by flowing into the cells when an action potential from a nerve cell reaches the plasma membrane of a muscle cell and triggers a change in membrane potential. This opens channels that let sodium in comes the sodium, and the result is a change in membrane potential, which initiates a series of events inside the cell that results in muscle contraction. Conduction of nerve impulses is also dependent on sodium influx. So again, a very important cation. Cations are positively charged ions, while anions are negatively charged ions. Sodium deficiencies are rare, especially in the U.S. They're characterized by persistent vomiting and diarrhea and excessive perspiration, where you lose 2 to 3% of your body weight or more. Depletion of sodium in the body can result in muscle cramps, nausea, vomiting, dizziness, shock, and coma. Normally, the kidney will respond by conserving sodium through the action of aldosterone on the functional unit of the kidney, which is called the nephron. Okay, where do we get our sodium in our food? Most sodium is added by food manufacturers and restaurants. We also find it in milk and dairy and in processed food. The sodium content of every food is listed on the label, and what you're looking at here is a breakdown of sodium content in food that's added, for instance, in restaurant meals. Here is what's added to foods during cooking in the home. Here what's added to food at the table, and here what's present in foods naturally. So again, you might wonder, well, is this a plot to make us all hypertensive? Because there is a correlation between excess sodium intake and hypertension. And the answer is no. The reason that we like sodium in our food is because it tastes good. And that's something that be attested to by anyone who's ever been on a low sodium diet. And what they'll tell you is that the food is basically relatively tasteless and unappetizing, so they tend to eat less of it. So often when people start dropping their blood pressure on a low salt diet, you can attribute it probably both to the loss of sodium in the diet, but also the loss of interest in the food. And that'll result in a reduced caloric intake and a decrease in obesity. And here you're just looking at food sources of sodium broken down by food item, sodium content in milligrams, and the percent daily value. And again, they're relating this all back to the food pyramid and the different groups, the grains, the veggies, the fruits, the oils, milk, and the meat and beans. Remember that we've shifted from the My Plate away from the My Pyramid as a less quantitative way to balance your diet, but a lot of the information in your text still refers back to the My Period diet plan. Okay, what are our sodium needs? Our AI is about 1.5 grams per adult. The body needs only 0.2 grams to function. Our daily value is 2.4 grams a day, and our upper level is 2.3 grams a day. Typical intake is almost double that, so sodium-sensitive individuals should restrict their intake. Potassium is a different story. It's also a positive ion in intracellular fluid, and it functions in fluid balance and nerve impulse transmission. It's also associated with lowering blood pressure. 90% of potassium is consumed, which is consumed is absorbed. Low blood potassium can result in muscle cramps, confusion, constipation, irregular heartbeat, arrhythmia, and or heart failure, myocardial infarction. Where do we get our potassiums in our diet? Fruits, vegetables, milk, grains, meats, dried beans. The AI is about 4.7 grams a day, and the daily value is about 3.5 grams a day, and a typical intake is between 2 and 3 grams a day. Diuretics may deplete potassium, so it has to be restored in the food that we eat. Excess potassium is excreted by the kidneys, and as a result, there is no upper level. And here you can see a breakdown of different types of food, their potassium content, and the percent daily value on the far right-hand side. And again, use the key at the bottom to break it down by food type. Okay, let's talk about some anions for a moment. Let's talk about chloride. It's a negative ion for extracellular fluid, and it's a component of sodium chloride or table salt. It's also found in hydrochloric acid. Its functions are in the immune response and in nerve function. And you might wonder, well, why did I mention hydrochloric acid? What relevance does that have to human physiology? Well, hydrochloric acid is secreted by the stomach as an effort to digest the food that you eat. It's manufactured by specialized cells in the stomach lining, which are able to transport actively chloride and protons into the stomach lumen, and there they essentially associate with each other because of the fact that opposite charges will attract, and they form hydrochloric acid in solution. And this is a powerful hydrolytic liquid that can break down fats, starches, proteins, and so forth. So we produce lots of hydrochloric acid every day. As long as it stays in the stomach, we're in good shape. It's when hydrochloric acid leaves the confines of the stomach, either as a result of acid reflux disease or an incompetent sphincter, either at the superior aspect or inferior aspect of the stomach, that we can experience ulcerations as a result of having acidic components leave the stomach and enter, for instance, the esophagus, where they will produce esophageal ulceration, or if we have a malfunctioning pancreas and the chyme from the stomach empties into the small intestine and adequate amounts of bicarbonate are not secreted in the pancreatic juice, which is what is essentially used by the body to neutralize stomach acid, it can result in ulceration of the duodenum. So a couple of things to be aware of. It's a powerful corrosive compound. If you got it on your skin, it would eat a hole right through it. It's very, very powerful stuff. What are our chloride needs? Well, excesses are excreted by the kidneys, and our AI is about 2.3 grams a day, with our daily value being 3.4 grams. The upper level is 3.6 grams, and high intake may cause high blood pressure. Why? Well, because again, water chases solutes, and if you have a consistently high salt intake, the kidneys can sometimes be overwhelmed and not excrete enough of the sodium to compensate for what you're consuming in your diet, and so you can have transiently high blood pressure. Now, over time, what will happen is that the kidneys will catch up and they will even out the electrolyte concentrations of sodium, chloride, potassium, and so forth, and so that this won't be a chronic condition unless your kidneys aren't functioning as they should, and the result then could be an extended hypertensive state. Okay, calcium. 99% of it is found in the bones and the teeth, and it makes up about 40% of all the minerals present in the body. It is a structural component of mineralized bone, and as a result, your skeletal system serves as a mineral storehouse of calcium, of phosphate, but also of trace minerals as well. It lends hardness to the skeletal system. Calcium phosphate is the chemical form in which we find most of the calcium in the body. How do we absorb calcium? Well, the amount in the body is dependent on how much we absorb in the diet. It requires the slightly acidic environment in the GI as well as active vitamin D. It's absorbed in the upper part of the small intestine, which is called the duodenum. Normally, this absorbs about 25% of the calcium in our food. It increases to about 60% during times of need, such as in pregnancy and infancy, which is when what's happening? We're building a new skeletal system, so it's not a surprise that we need more calcium per unit time. Parathyroid hormone is one of the hormones that regulates calcium balance, and what parathyroid hormone does is demineralizes bone and puts free calcium into the blood. And so individuals that have an overactive parathyroid can experience osteoporosis, okay, a loss of bone density. Hormones that counteract the activity of parathyroid hormone are calcitonin, is one example, which tends to put calcium back into bone. Okay, decreased absorption of calcium can be a result of rapid intestinal motility, high fiber intake, excess phosphorus, active vitamin D deficiency. Let's be very clear about that. And polyphenols, which are often found in tea. Also, menopause will have an effect on this, in addition to aging. How do we regulate blood calcium? The blood level is maintained at the price of the bone. The bone is the storehouse for calcium in our bodies. Blood level can be maintained despite inadequate calcium intake, and what you do is you get it from the skeletal system if you don't take it into your diet. This can set the stage for future bone fractures as bone becomes less and less dense. What does calcium do? It aids in bone formation and maintenance. It's also involved in blood clotting. If you don't have adequate calcium in your serum, your blood won't clot and you'll bleed out. It's also involved in nerve impulse transmission, specifically when the action potential reaches the end of the nerve cell, which is called a neuron. What happens is that an influx of calcium into the axon terminal results in the fusion of vesicles that contain neurotransmitters with the synaptic bouton, which is the very tail end of the neuron. As a result, neurotransmitters are secreted into the synapse, which is the physical space that exists between either one nerve cell and another nerve cell, or a nerve cell and a muscle cell. And those neurotransmitters then bind onto receptors of the postsynaptic membrane and induce a change in membrane potential on the cell that's downstream. Okay, so this is a very important biological function for this particular mineral. As we also already stated, it's involved in muscle contraction. It's also involved in cell metabolism because it can activate various enzymes intracellularly. Okay, it can serve as a cofactor. Okay, how do we build higher bone mass? Well, we have adequate absorption in the diet. We also maintain a healthy body weight. Normal menses is also important. And we also want to engage in weight-bearing physical activity because bone is living tissue and it responds to force applied to it by becoming more dense along the lines of force. Moderate intakes of protein, phosphorus, sodium, and caffeine also maintain high bone mass. We also don't want to smoke, and we want to reduce our use of certain medications in order to allow bone to adequately mineralize. What else does calcium do? It may lower blood pressure, it may reduce colon cancer, it may reduce PMS symptoms, It may lower blood cholesterol, it may reduce kidney stones, and it can reduce lead absorption and promote weight loss. Now, see the qualifier in front of all these? May? Okay, what does that mean? It means that there's correlative evidence. Okay, remember the difference between correlation and causality. In correlation, what you have is one thing occurring when something else occurs uh, with a very high coincidence. Doesn't happen every time, but can happen a significant percentage of the time. What's causality? Causality means that one thing happens because the other thing makes it happen, and there's always a 100% correlation. So again, take these claims with a little bit of skepticism and investigate for yourself the evidence that's out there that indicates all these possible roles for calcium. Okay, where do we get our calcium? Dairy, meat. And you can see here the breakdown. There's your adequate intake. This is the number of milligrams of calcium in each. And these are the distributions of the food groups. And notice that we predominate with dairy, the milk here in the aquamarine. And we get a significant amount in meat as well. Okay, you can see meat here and here. There's some in fruit. And so, again, not a surprise. If you have your dairy and your meat, you're going to meet your calcium needs relatively easily. Okay. Bone strength is dependent on bone mass and mineral density. The more there is, the stronger the bone. Bone is an interesting composite of protein and calcium phosphate. The calcium phosphate lends hardness to the bone so it can resist forces of compression, while the collagen resists twisting or torsional forces. And this is very similar to the way that you build a concrete superstructure or the way fiberglass is arranged. As a result of having two different components that each provide different strengths and by the same token don't share weaknesses, you produce a single structure that is much more structurally sound than either of the two components would be on their own. What are our needs? Daily value is about a gram a day. AI is about 1 to 1.2 grams a day for adults and 1.3 grams a day for adolescents. Why? They're growing. Their skeletal systems are in a state of biosynthesis. Average intake is about 0.8 grams per day for women and 1 gram a day per men. Again, men requiring more because they're bigger. Okay, more metabolism, more processes that need calcium, also a larger skeletal system to maintain, and as a result, men require more overall calcium. The upper level is about 2.5 grams a day. Supplements are recommended for people who can't incorporate calcium into their diet, but they're not recommended with high zinc meals. Calcium carbonate, which is 40% calcium, is recommended for those with ample stomach acid, and this is found in antacids such as Tums. Calcium citrate, which is 21% calcium, enhances absorption due to the acidity content and is usually recommended for older adults. Citracal is an example. Okay, phosphorus is a major ion in the intracellular fluid. It provides bone and tooth strength because calcium phosphate is the mineral component of bone that provides compression strength. And so the phosphorus goes hand in hand with the calcium. It's also a component of various compounds. We find it in ATP, cell membranes, enzymes, and DNA. So it's a pretty important component. What is its role in acid-base balance? Well, it's a buffer. Okay, so when phosphorus is in free solution, it tends to have a negative charge, which means phosphorus will tend to raise the pH of solutions in which it's found. And what it'll do is, if it's present in a solution, the solution will tend to resist pH challenges, and as a result, keep the body's fluids within a very tight pH range, which is important for homeostasis. The absorption is based on the body's needs. Generally, we absorb about 70 to 90%. There is no disease associated with deficiency as of yet. It may contribute to bone loss in older women, however. Vitamin D, remember, enhances absorption of calcium and also, incidentally, of phosphorus. Okay, where do we get it? In a wide variety of foods: dairy, bakery products, eggs, sodas, and meats. Some food additives. It's difficult to limit our intake. The RDA is about 0.7 grams a day for an adult. Daily value is about a gram a day. Current intake usually exceeds the RDA, but a deficiency is not likely. Is there such a thing as phosphorus toxicity? Of course, there can be toxicities for any compound. It can be a problem for individuals with inefficient kidney function. Phosphate ions bind to calcium, and a chronic imbalance can lead to bone loss. Upper level is about 3 to 4 grams a day. Magnesium is also a very important mineral. It's a cofactor. Absorption is based on the body's needs. Usually about 40 to 60% is absorbed. Our kidneys regulate blood concentrations of magnesium, and 60% of it is stored in bone. So here you can see again that the skeletal system is a mineral storehouse. What does it do? It aids in enzyme reactions, so it's a cofactor. It also helps in potassium and calcium metabolism and in proper nerve and cardiac function. It also regulates insulin release from the pancreas, and it may dilate arteries and as a result decrease blood pressure and may prevent heart rhythm abnormalities. Again, note the may here. So take it with, no pun intended, a grain of salt. Okay, deficiencies can develop slowly, can result in an irregular heartbeat, can also be characterized by weakness, muscle spasms, disorientation, nausea, vomiting, and seizures. Too much or too little magnesium? Well, magnesium loss can be affected by heavy perspiration, diarrhea and vomiting, alcoholism, and it can be characterized by disorientation, weakness, muscle pain, and poor heart function. Toxicity is generally caused by medications that control the rate at which magnesium is lost or retained. Okay, where do we get it? Whole grains, vegetables, nuts, and seeds, hard tap water, dairy, chocolate, and meat. The RDA for women is 310 milligrams a day, and for men it's about 400 milligrams a day, with our daily value being 400 milligrams a day. Average intake is lower than the RDA, and the upper level is about 350 milligrams in non-food sources. Okay, sulfur. And you might think, sulfur? What in the heck does sulfur do? Well, it turns out sulfur is an important component of a couple of amino acids, cysteine and methionine. And one of the things that sulfur does is it can act as an antioxidant if it's in the form of sulfhydryl groups. But the other thing that it does is it can produce covalent bonds in proteins, which can contribute to changes in secondary structure. And of course, protein structure is important to protein function. So we want to be aware of that. It's important also in acid-base balance, and it's also helpful in drug detoxifying pathways. It's part of a natural diet, primarily coming from protein, and it's used to preserve foods. And there are no known deficiencies or toxicities yet. Okay, the trace minerals are needed in much smaller amounts, but they're essential for our health and difficult to study because they're present in such small quantities. Animal sources of mineral are generally better absorbed than plant. Iron is one of these trace minerals. It's found in minute amounts in every cell. 18% of it is absorbed. We want to differentiate between heme versus non-heme iron. Heme iron is found in animal products and is better absorbed than non-heme. Heme looks like, if I were to draw it, a spider web almost, and it's basically a collection of carbon-carbon double and single bonds spread out in a real pretty arrangement. It looks almost like a snowflake. You can probably find a picture of it in your textbook. If not, I can show it to you. And in the middle of the heme sits an iron atom, and as a result, we have transport proteins in our bodies that are more apt to bind to and move heme associated with iron around than just free iron. Iron's a little bit tougher to absorb straight. Meat protein factor may also aid in non-heme absorption. Vitamin C also enhances absorption of non-heme iron. The absorption of iron is determined by the body's needs. It's stored in intestinal cells and absorbed in an acidic environment. It's centered by phytic acid, oxalic acid, high fiber, high calcium polyphenols. You might wonder, well, what do all those things have in common? Well, a lot of them are chelators, and what a chelator is an organic compound that will sort of wrap around a cation like a claw and take it out of solution so that it's more difficult to transport or absorb. These other components, high fiber, high calcium, they're probably, the fiber probably simply associates very easily with the iron and hinders its ability to be free in solution. High calcium probably competes with iron for binding sites in the GI for absorption. And polyphenols are similar to what the oxalates and the phytic acids do. What they do is they box the iron up so that it's more difficult to absorb across the GI. Okay, this is just a little video on.
When old red blood cells rupture, the released hemoglobin is ingested by macrophages. The globin chains of hemoglobin are broken down to individual amino acids that are metabolized or used to build new proteins. Iron is released from the heme of hemoglobin. The remaining structure is converted to biliverdin, which is then converted into bilirubin. Iron is transported by transferrin in the blood to various tissues for storage, or to red bone marrow for making new hemoglobin. Free bilirubin is transported by albumin in the blood to the liver. Liver cells make conjugated bilirubin, which is excreted as part of the bile into the small intestine. Intestinal bacteria convert bilirubin into bilirubin derivatives, which contribute to the color of feces. Some of the bilirubin derivatives are absorbed into the blood and excreted from the kidneys in the urine.
Okay, what are some functions of iron? Well, it's involved in hemoglobin and red blood cells. It transports oxygen and CO2. It has a very high turnover rate, and we have a very high demand for iron. It's also found in myoglobin and muscle cells, which is very similar to hemoglobin. It actually has a higher affinity for oxygen than hemoglobin does, and this is why it's present in muscle tissue, so that it can take oxygen from blood very easily, and as well as iron, and store it inside the muscle tissue so that the muscle tissue can use it in oxidative metabolism. It's also a component of the electron transport chain, which is a series of reactions that take place in the inner mitochondrial membrane that result in the oxidation of compounds such as FADH2 and NADH into NAD and FAD, and the electrons that are taken from those reduced compounds are passed through a series of carriers in the inner mitochondrial membrane, and the energy that's lost as they're passed from carrier to carrier is captured and used to generate a proton gradient inside the mitochondria, which is used to synthesize massive amounts of ATP. And I'll sketch this out for you when I see you in lecture Wednesday night. Okay, it's an enzyme cofactor as well. It also aids in immune function, and it also acts as in drug detoxification pathways. Iron deficient anemia is the most common form, results in low levels of hemoglobin and hematocrit, results from insufficient intake and stores, and can be characterized by a reduction in the production of red blood cells and a reduction in oxygen carrying capacity. Most at risk are infant, toddlers, those with chronic blood loss, vegans, runners, and women in childbearing years. It can result in pica in women and children. Signs are paleness, brittle nails, fatigue, poor temperature control, and poor growth. And these are the food sources of iron. Again, the RDA on the left, the amount of iron in milligrams in this column here, and then two columns, one for the adult male and one for the adult female, showing you, again, the percent RDA that each of these food groups has in our diet. And note that, again, for the male, we require more than the female does. And the reason for that, again, is because the male is more metabolically active. There's generally more body mass, there's more lean muscle mass, and as a result, there's a greater need for the components of oxidative metabolism, and as a result, there's a greater demand for total iron. Okay, the RDA is 8 milligrams a day for an adult male, and it's 18 milligrams a day for an adult female aged 19 to 50. And now this seems a little counterintuitive. We just got finished saying that men need more. Why do women have a higher RDA? Well, because women, especially women who are not menopausal, have a cyclic loss of iron with every menstrual period, and so it has to be replenished in the diet to account for the amount of iron lost at menses. Daily value is 18 milligrams a day, and the average intake exceeds the RDA for men, and it's low for some women. The upper level is 45 milligrams per day. You can obviously have iron toxicity, as you can have toxicity in any mineral. It can be serious, especially for children. Signs are diarrhea, constipation, nausea, abdominal pain. It can cause death due to respiratory collapse, which can result in shock. Hemochromatosis is a genetic disease in which iron deposits can lead to organ damage, and it may go undetected until organ damage becomes acute between ages 50 and 60. And this is actually an interesting condition because iron will accumulate in the fluids of individuals with this particular genetic disease, and it can set off metal detectors in airports. If you look at zinc, absorption is influenced by the food that we eat. Animal sources, again, are better absorbed, and it's dependent on the body's need for that mineral. Factors that decrease absorption are the presence of phytic acid. It also competes with copper and iron for absorption. Why? Because it's also a cation. It's about the same size. So what it'll do is it'll fight for those absorptive slots in the GI and can inhibit the absorption of those other cations. What does it do? It's a cofactor to many enzymes. It is also involved in DNA synthesis and function. It also aids in growth, protein metabolism, and wound healing, aids in immune function, aids in cell membrane structure and function, and the development of sexual organs and bones, and proper insulin regulation and insulin function. It's also a component of superoxide dismutase, and you might think, what in the world is superoxide dismutase? Well, it's an enzyme that uses zinc as a cofactor, and it destroys free radicals. And what free radicals do are break apart chemical bonds in other molecules, causing them to break down structurally. And this can have disastrous consequences for cellular structure and function. If you look at the food sources of zinc, again, you can see that the male, in this case, needs less than the female on average. Okay, and you can see the major sources of zinc are going to be meats and beans, followed by, I would say, dairy, form of milk, and then coming up in the rear would be grains, and then at the very end would be oils. What are our needs? Well, the RDA is 8 milligrams for an adult female per day and 11 milligrams for an adult male, where the daily value is about 15 milligrams per day. The average intake meets the RDA, and the upper level is about 40 milligrams per day. What are the results of toxicity? Well, it inhibits copper metabolism, and it could increase the risk for prostate cancer, and can cause diarrhea, cramps, nausea, and vomiting, and it can also suppress immune function. Selenium is another trace element. It's readily absorbed and excreted through the urine and feces. It's a cofactor for glutathione peroxidase. It protects the heart and other cells from oxidative damage, and it works together with vitamin E. And it could aid in cancer prevention, but the evidence there is correlative and not causal. It also is important in thyroid hormone metabolism. What does deficiency result in? Muscle pain and wasting, weakness, and deterioration of the heart muscle. What are our sources and our needs? Well, our sources are fish, meat, eggs, milk, and shellfish, grains, seeds, and nuts. The RDA is 55 micrograms per day for selenium. Microgram is 1 times 10 to the minus ninth grams. It's a very tiny amount. And the daily value is 70 micrograms per day. The average intake usually exceeds the RDA and the daily value. What does selenium toxicity look like? Well, it's characterized by an upper level of 400 micrograms per day or greater. You tend to have a garlicky breath, hair loss, nausea, vomiting, weakness, rashes, and cirrhosis of the liver, which is not a good thing. The liver is a very important organ in the body. It actually gets its nickname liver from to live, right? It keeps us alive, and it synthesizes bile salts. It's involved in glucose metabolism. It's also a major detoxifier and a major blood protein manufacturer. So you lose your liver, you lose a lot. Okay, iodide. It's found in foods, usually in iodized salt. It supports thyroid hormone synthesis. In fact, it is a structural component of thyroid hormone. This regulates the metabolic rate as well as growth and development. Deficiencies can result in goiter due to low intake. Deficiencies in youth, specifically during development, can result in cretinism, which is a stunting of fetal growth and mental development as a result of low iodide in the maternal diet. You might wonder, well, gee, why is it just a metabolic impact in the adult, and in fetal development you have these profound effects on the nervous system, the IQ, and so forth? And that's because during fetal development, what you're doing is laying the foundation for multiple organ systems and tissues. And if you perturb that in any way, it can result in multi-system dysfunction in the adult. So again, this is another example of what I like to call pleiotropy. It's not the size of the mistake as much as the timing of the mistake that eventually dictates the magnitude of the impact of that mistake. And if you have a problem with iodine levels in embryonic or fetal development, the result can be profound. It can affect many organ systems and many tissues. Okay, what are our sources and needs? Iodized salt, about a half teaspoon meets the RDA. Saltwater fish, seafood, and dairy and grains usually are nice sources. Sea salt actually is a poor source. Iodide is usually lost during the processing of sea salt. Plant sources can depend on the soil content. The RDA and the daily value about 150 micrograms per day, but only 50 micrograms are needed to prevent goiter, with an average intake that generally exceeds the RDA. What does toxicity look like? Well, an upper level is 1.1 milligrams per day. Thyroid hormone can become inhibited. Its synthesis can be inhibited if you exceed this upper level. Toxic goiter can result. Excess consumption of seaweed can pose a risk because seaweed contains lots of iodine. Okay, copper. It aids in iron metabolism. The absorption, again, is dependent on the body's needs. It decreases with high intakes of vitamin C, phytic acid, fiber, zinc, iron, and certain amino acids. What are its functions? It increases iron absorption. It aids in the formation of connective tissue. It's found in superoxide dismutase. It assists the immune system It assists in blood clotting. It aids in brain development in embryonic and fetal stages, and it aids in cholesterol metabolism. Deficiencies can result in anemia and a decreased white count, as well as bone loss and inadequate growth. What are our sources? Organ meats, seafood, cocoa, mushrooms, legumes, seeds, nuts, and whole grains. The RDA is about 0.9 milligrams per day for adult, and daily value is 2 milligrams. And the average intake is usually near the RDA, with an upper level of 10 milligrams per day. Okay, fluoride. The reason that we put fluoride in drinking water is to prevent cavities. It helps tooth and enamel resist the corrosive effect of acids produced by the bacteria in your mouth that feed off of the sugar left in the saliva. And it also inhibits overall bacterial growth. What are our sources? Fluoridated water, which has about 0.2 milligrams per cup. which is about the same as 1 part per million. We also find it in tea, seafood, and seaweed, and toothpaste. Adequate intake is 3.1 to 3.8 milligrams per day for adults. Toxicity can result in mottling of teeth in children. We want to limit toothpaste to pea sizes for children because high amounts can actually weaken the teeth. And the upper level is 1.3 to 2.2 milligrams a day for children, with an upper level of 10 grams per day for older children and adults. Chromium enhances insulin action. It could have a role in type 2 diabetes, which is the adult onset type. It can result in low intake in impaired glucose tolerance and elevated blood cholesterol and triglycerides. We don't have much information on the sources. It's found in egg yolk, bran, whole grains, cereal, organ meats, meat, and beer. The plant sources are dependent on the soil content. An adequate intake is, let's call it 30 micrograms a day for adults. A daily value set at 120 micrograms per day, with an average intake of 30 micrograms per day. There's no toxicity from food and no upper level. Exposure to chromium in environmental waste sites is probably the major source of toxicity if it were to manifest itself. Can result in lung and liver damage. Okay, manganese. It's a cofactor in carbohydrate metabolism and a component of superoxide dismutase, and has a role in bone formation. There are no deficiency symptoms observed in humans. The AI is about, call it 2 milligrams per day. Average intake usually meets the AI, and the daily value is 2 milligrams per day. Toxicity in individuals working in manganese mines is characterized by psychiatric abnormalities, violence, and impaired muscle control. The upper level is 11 milligrams per day. Molybdenum is required by several enzymes as a cofactor. Deficiencies are rare. Deficiencies are characterized by increased heart and respiratory rates, night blindness, mental confusion, edema, weakness, and coma. The RDA is 45 micrograms per day with a daily value of 75 micrograms per day and an AI of, call it 90 micrograms per day. Upper level is 2 milligrams per day. Here you can just see a list of the minerals and their various functions. So this is a nice summary slide. This is available in your text. And then this is just a look at the MyPyramid sources of minerals as broken down by class of food: grains, vegetables, fruits, oils, milk, meat, and beans, and the particular food items that would carry the particular minerals that would be carried by each of these food items. And so notable is that oil contains no minerals, right, because it's simply lipid. Okay, some other minerals of note are boron, nickel, silicon, vanadium, arsenic. Believe it or not, we need a little bit of arsenic. Too much will kill you, but trace amounts are important. Hypertension is characterized by a higher than average systolic over diastolic blood pressure. Your systolic pressure is the pressure in the vessels when the ventricles are squeezing, whereas the diastolic pressure is the pressure in the ventricles, the pressure in the blood vessels when the ventricles are relaxing. And so if you have consistently high blood pressure, what that generally means is that you either are obese, you may have a problem with salt balance, or a combination of the two, or you may be suffering from arteriosclerosis. And in either case, this is a problem because consistently high blood pressure can burst vessels, and downstream tissue can die as a result of loss of blood and oxygen, as well as nutrients. So we want to be aware of hypertension. Optimal BP is less than 120 over 80 millimeters of mercury. Sustained systolic pressure is greater than 139 millimeters of mercury, or diastolic pressure greater than 89 millimeters of mercury over a reading that is taken under different conditions over a series of days, not just one single reading. 95% of all hypertensives have no clear cause. It could be either primary or secondary hypertension. Secondary hypertension is the type of hypertension that is thought to be brought on by lifestyle. Primary hypertension is relatively straightforward and has to do with hormone and kidney malfunction. Okay, why do we need to control blood pressure? Well, it's a silent killer. To prevent the disastrous consequence of high blood pressure, which is a burst capillary bed in the brain or in the heart, what we can do is we can exercise, we can reduce our fat intake, and we can reduce our overall body weight and increase our lean muscle mass. Lean muscle mass actually causes the body to lay down more blood vessels, which reduces overall blood pressure, because what it does is provides more avenues through which blood can flow, which will result in less drag on blood as it makes its way from the heart to the arteries to the capillary beds and then back to the veins and then eventually back to the heart. So how do we prevent chronic hypertension? Exercise, diet. This allows us to prevent cardiovascular disease, poor circulation, kidney disease, and stroke, which can result in a decline in brain function. African Americans are most at risk. What are some causes? Aging, family history, arteriosclerosis and obesity, elevated insulin, inactivity, excess alcohol intake. Of these, which can we control? Well, we can control obesity, we can control inactivity, we can control excess alcohol, and in a way, we can control arteriosclerosis and elevated insulin by modulating our diet. Elevated insulin, remember, is an outcome of a diet that's consistently high in carbohydrates. And so what you can do is reduce your glycemic index in the food that you eat and avoid those insulin spikes, and the result will be a more modulated insulin output and a more modulated insulin response. Okay, sodium and blood pressure. Blood pressure transiently increases with sodium intake, and fluid retention can lead to increased blood volume. But what happens? The kidneys compensate for that. So sodium and hypertension is particularly of note in individuals with kidney disease. Other minerals can affect hypertension. Greater than 100 or 1,000 milligrams per day can lower blood pressure. 2 to 4 grams of potassium per day can also lower blood pressure, and magnesium can lower blood pressure. The DASH diet is one of these diets that stresses a reduction in sodium and an increase in these other minerals in order to maintain a healthy overall blood pressure. It's a diet rich in fruits and vegetables and also rich in vitamin C. What are some medications that affect hypertension? Diuretics reduce blood volume and increase urine output, and as a result drop high blood pressure. Other medications can slow the heart rate and relax the blood vessels. This is called vasodilation. This also can result in a systemic lowering of the blood pressure. Osteoporosis is an outcome of calcium deficiency and inactivity. It's a pediatric disease with geriatric consequences and leads to about 2 million fractures a year. Slender, inactive women who smoke are most at risk. They tend to lose bone density, and as a result, the bones are easier to break and shatter. And here you can see an example of a young and an elderly woman who is suffering kyphosis as a result of osteoporosis in the vertebral column. So what you do is you lose height, you lose bone density, and you're prone to bone.
Bones grow through the process of appositional growth, the formation of new bone on the surface of older bone or cartilage. Osteoblasts beneath the periosteum lay down bone to form ridges around a blood vessel. The blood vessel lies in a groove between the ridges. The groove is transformed into a tunnel when the bone built on the adjacent ridges meets. The periosteum of the groove becomes the endosteum of the tunnel. Osteoblasts from the endosteum lay down bone to form a new concentric lamella. The production of additional concentric lamellae fills in the tunnel and completes the formation of a new osteon.
And here's a look at bone structure. What you're seeing here is a long bone. Notice that you have an outer layer of compact bone with a deeper layer of spongy bone, which is lightweight and powerful. And then deep inside we have the bone marrow. And in long bones, this is yellow marrow made up primarily of adipose tissue, whereas in bones such as the clavicle, the scapula, the ribs, and the hips, this is made up of red bone marrow, which is where we synthesize our red blood cells. Rapid and continual bone growth is seen throughout adolescence. They see a peak in bone mass. Bone growth and mass is also determined by gender, race, familial pattern, and other genetic factors, and it begins to lose its density after age 30 as a result of hormonal effects and also decreased activity levels. Women experience an increased bone loss after menopause because of the loss of the ovaries, which are a source of estrogen, which tend to mineralize bones. DEXA bone scans are usually recommended for women who are postmenopausal to make sure that they're not on the edge of becoming osteoporotic. This is table 9.5 out of your text that shows you positive diet and lifestyle factors, and then warning signs here for corrective action in activity level and diet, and then negative diet and lifestyle factors and their appropriate cautionary tales. Okay, so a nice little summary slide for everything we've talked about so far. And this is just a look at mineral bone density as we age, and you can see that it drops. What you're picking up here is the difference between an active individual and an inactive individual. And what you're looking at with these shaded areas are areas where bone density is being lost, and then areas where you're actually osteoporotic. Okay, so this will be the osteoporotic zone, this will be the low bone mineral density zone, and this will be healthy bone mineral density. And so in an individual with a relatively active lifestyle, you don't even hit low bone mineral density until you're well into your advanced years. And so again, activity can stave off some of the debilitating effects of osteoporosis.
Bone is living tissue. Bone building is far from complete when a baby is born. During growth, from infancy to adulthood, bone is increased in size, strength, and hardness. Also, in different parts of the body, bones grow at different rates. Bone growth is partly in response to stresses that are put on the bone by weight-bearing motion. The simple acts of walking, running, jumping, and lifting heavy objects put strain on bones that results in increased bone density. Trabecular bone is found in the shaft and at the ends of the long bones, inside the spinal vertebrae, and inside the flat bones of the pelvis. In the ends, trabecular bone completely fills the cavity, and its structure transmits stress forces to the shaft. Trabecular bone forms an internal scaffolding network for bone. The trusses and arches found within the trabecular bone provide for the great strength of bone and yet surprising lightness. The arches and trusses inside trabecular bone provide a sponge-like appearance in the bone and also create the opportunity for blood vessels to penetrate the bone structure from the center core, marrow, of the long bone. Bone remodeling is such a thorough process that one's entire bone structure is replaced approximately every 10 years. Once maturity is reached, about age 30, the process of remodeling slows, and the loss of bone calcium deposits exceeds the replacement of the bone structure. Beyond this point, it is no longer possible to substantially increase bone density. Over time, the density of the arches and trusses diminishes, and the spaces between them become larger. This process leads to a general weakening of the bone structure. It is a very gradual process and requires decades before any noticeable bone weakness appears. Osteoporosis is the end result of the erosion of the arches and trusses. Osteoporotic bone has much larger spaces between the arches and trusses and is significantly weaker than normal bone. Therefore, it is more prone to fracture. This condition is responsible for many injuries related to falls in elderly people. Women are more susceptible to osteoporosis than men. This is probably related to hormonal influence on bone growth and calcification. Also, dietary intake of calcium and other nutrients, including protein, phosphorus, vitamin A, vitamin D, vitamin K, magnesium, zinc, and copper will influence bone density, in that deficiencies will cause decreases. Finally, genetics have an influence on bone density. Here is the progress of bone loss in a person who has taken some precautions related to osteoporosis onset. Note that as the aging process continues, the rate of erosion of the trabecular structure has slowed, and the end result at age 70 is bone that is stronger and denser than a bone with severe osteoporosis. Strategies for preventing osteoporosis are different for young women and older women. Young women should be sure to meet their needs for calcium, vitamin D, and other nutrients. Physical activity of a weight-bearing nature is also important to maintain bone mass. In postmenopausal women, estrogens, estrogen receptor modulators, and calcitonin can slow bone turnover by binding to bone receptors. Calcium supplementation and regular exercise, especially weight-bearing and resistance activities, are important strategies for older people. Finally, since both tobacco smoking and alcohol consumption have negative effects on bone growth, these behaviors should be avoided for healthy bones. In summary, osteoporosis, the weakening of bones due to loss of calcium and phosphorus from the interior of the bone architecture, is a degenerative disease that is influenced by many contributing factors. Health-promoting interventions such as adequate nutrition and physical activity, and medical interventions such as prescription medications designed to limit progress of osteoporosis, coupled with positive behaviors such as not smoking or using alcohol excessively, can forestall the onset and severity of osteoporosis. Men are also at risk for developing osteoporosis. For men, similar prevention strategies apply. These include adequate calcium, vitamin D, and other nutrients, physical activity of a weight-bearing nature, and avoidance of behaviors like smoking and excessive alcohol consumption.
Although she's only 33, Carrie Botel has already broken several bones, and a test shows her at risk of osteoporosis.
They told me I basically had the bones of an 80-year-old.
And today, this landmark report from the U.S. Surgeon General warns there are 10 million Americans with osteoporosis and another 34 million at risk because of low bone mass. Devastating because 20% of seniors who break a hip die within a year. Another 20% go to a nursing home. And 33% of those who break hips are men.
Osteoporosis just isn't your grandmother's disease. We all need to take better care of our bones.
What to do? For calcium, drink milk or take supplements. Get vitamin D and exercise. Even young people, because we build bone until age 30 and then start losing.
You're going to lose 40 to 50% of your bone mass just by virtue of aging. In addition, women have menopause, and during those 5 years, they will lose another 15 to 20% of their bone mass.
And with the graying of America, the report warns by 2020, half of all those over age 50 could be at risk. Robert Hager, NBC News, Washington.